So in this set of Snap Circuits videos, we're looking at projects 535 to project 547. So, project 535 is the Machine Siren. There it is in the book, and here it is on the board. And so with this circuit, we're making use of our alarm IC. Let me take this iron core rod out for the moment. And we're outputting our alarm IC through our electromagnet in series with the speaker. So we're getting the output of the alarm IC through a speaker here, but it's going to pass through our electromagnet first. So it's going to charge it up and affect the output there. And then we sort of have a filter circuit here with our C2 capacitor and our press switch, which we can then turn on, and it will kind of help filter out any of the electromagnet's effects. So when we turn the slide switch on, we get our police siren sound effect because we're using the middle input of our alarm IC. And you can tell it's not as loud as it usually is because, again, it's passing through an inductor here with our electromagnet. But if we add our capacitor in there with it, it gets louder. So the capacitor being added into the circuit there helps kind of filter out the effects of the electromagnet, restoring the amplitude of the alarm IC's output there. Now, an interesting thing that's not mentioned in the book is if you use the iron core rod in the electromagnet. I want you to listen to the output of the speaker there with the siren as I put this iron core rod into the electromagnet. Notice how the sound is changing. I'm just going to drop it in there now. And now you notice the siren is a lot quieter. And that's because we have a ferrous iron core rod here that the electromagnet is now acting upon. Basically turning that iron core rod into a little bit of a magnet. Though it's not very strong at the moment. But it is having an effect again on the output, because now we're doing something with that iron core rod with the electromagnet. Of course, when I take it out, well, now the electromagnet's no longer acting upon it, so the sound comes back up. But it didn't. But as we insert the rod, it starts to act on it, and we change the output there a little bit. And depending on where the rod is, I can sort of get it to manipulate different outputs of the alarm IC. So that's project 535. So now we're going to move on to project 536, which is Hear the Motor. So here we are with project 536, Hear the Motor. There it is in the book, and here it is on the board. And this is another one of those suggested projects, as pointed out right here. And I believe that we've done a project very similar to this in the past with the previous Snap Circuits. Although I couldn't find anything specific on it, but we certainly worked with circuits that did what this one is demonstrating here. So it's pretty simple. We have our speaker in series with our motor, and then we have our press switch to power on and off the circuit. Since this is a pretty small circuit, I'll go ahead and bring the camera down in here. About there. And when we press the press switch, our motor spins up. But because the speaker is in series with the motor, it, of course, reduces the overall motor power, but we also hear the motor running through the speaker there. And the reason for that is what we've seen in previous projects, especially when we use the transformer with the motor on the input side of it, is that the motor is very quickly turning on and off, basically breaking contacts inside there as it turns. And because of that, we get a pulsed waveform output here, which we can hear through the speaker as the sound. And if we slow the motor down, the sound, of course, will change with it. chart get a little stuck on the camera here. Back up. There we go. There. So that is project 536, and now we're going to look at project 537, which is back EMF. So here we are with project 537, back EMF. There it is on the book, and here it is on the board. Now, since we're using 6 volts through our adapter here, I've simplified the circuit by just taking the 3 snap, and of course we're going to need the extra battery in there, so pretty simple. So let me bring this in nice and close here. Bring it up a little bit more. There we go. And so we've got 6 volts coming out, going through our slide switch, which is in series with our 6-volt lamp, and which is in series with our motor. So with the back EMF, or electromagnetic force, with the fan on our motor, if we turn our circuit on, our fan spins up, and you see that our 6-volt light is pretty bright there. And that's because right now with the fan there, the motor is under load. So the back EMF on the motor right now is low, and because of that, it of course gets high current through there, and that's why we get a nice bright lamp. Now if we take the fan off, now we're going to create high back EMF, and because of that, it's going to create low current. So not enough current's going to go through our 6-volt lamp, so when we turn our circuit on this time, our motor spins pretty quick there because it's not under load, and you see that our 6-volt lamp there is glowing pretty dim. Again, the back EMF on the motor is high, so there's not a lot of current going through the overall circuit until we load the motor down. And if we stop the motor, well, now there's practically very little back EMF, so now the light is nice and bright. And of course, if I let the motor spin up some, you'll see the lamp go down as we create some back EMF there, letting the motor spin. Come back up here. Turned. So that's project 537, so now we're going to modify it for project 538, which is back EMF 2. So here we are with project 538, back EMF 2. There it is in the book, and here it is on the board. And again, I've slightly modified it because we don't need the other battery box and all, but it's similar to the previous projects, but this time we've added our NPN transistor with our 2.5-volt lamp in line with the motor there. So we still have our 6-volt lamp in series with our motor, just like the previous project. But now we have an additional leg where we have our NPN transistor being controlled by a photoresistor just off to the side here, and then that travels through our 2.5-volt lamp in series with our motor. So when we turn this circuit on, I can just cover this up. We turn it on, it acts like the previous project there with the 6-volt lamp glowing fairly bright there and our motor running. Now if I let a little bit of light in here, it may not be as noticeable. You may, if you were listening closely, hear the motor speed up a little bit. Let's see if it slows back down. Slows down just a little. And you may again hear it speed back up. You may not see much change in the 6-volt lamp, but you can certainly tell that the motor is speeding up and slowing down as I am covering up the photoresistor here and then letting some light into it. And that's because the NPN transistor here again is being controlled by our photoresistor. So we're letting just a little bit of current flow through the NPN transistor here and through our 2.5-volt lamp, even though it's not lighting. And that's providing an additional current path for our motor there. So by doing that, the motor starts to get additional power to it. And again, we're still looking at the back EMF off the motor here, and because the motor starts getting more power, it starts turning faster. And because of that, the back EMF on our 6-volt lamp here increases, therefore less current goes to the 6-volt lamp, and the 6-volt lamp starts to go dim. And of course we can certainly show this effect more with a flashlight. So I'm going to apply light directly on the photoresistor and we'll see this effect much more pronounced. See the motor start to speed up. And I don't know how well the 6-volt lamp is showing there, but the 6-volt lamp goes down in brightness, of course, as the 2.5-volt lamp gets enough current for it to start lighting up. And again, of course, you also hear that the motor also spins faster, because now it's got more current going through it. So that's how that project works. Now I gotta get back to the page I was at. So that was 538. So now we're going to look at project 539, which is electronic sound. So here we have project 539, the electronic sound. There it is in the book, and here it is on the board. So we got ourselves another oscillator circuit here, making use of our NPN transistor, our 5.1K, 100K resistors, along with our C1 and C2 microfarad capacitors. And then of course we get our transformer outputting to our speaker, and because of how the transformer is oriented, we are scaling down. So when we turn the circuit on, it produces a fairly modest frequency tone there. And again, it's just using capacitor C1 for the oscillation right now, because C2 is not connected until we press the press switch to put these two capacitors in parallel. Then we press the press switch. There's more capacitance there, so the circuit now oscillates at a lower rate. So we get a lower frequency out of the speaker there. Release the press switch, get less capacitance, and now it oscillates at a faster rate, so higher frequency. Lower frequency, higher frequency. And of course we can adjust the rate of oscillation, and thus the output frequency, by putting in our 10 microfarad capacitor, putting the plus side over here because that's where positive voltage is. And now it's oscillating to the point where it's kind of a fast ticking sound instead of more of a continuous tone like before. So that's how project 539 works. Now we're going to move on to project 540, which is electronic sound 2. And by that we're going to change our resistor around. So I'm going to put the original C2 capacitor back in its place. And we'll change the resistor, and by changing the resistance we can also change the oscillation in the circuit. So the 100K comes out, and now we're going to replace it with the 10K resistor. So we're going to reduce the resistance by a factor of 10, because we're going from 100K to 10K. So that's a 10-point reduction. So we'll go back here, plug that in. Now we turn the circuit on. We don't get anything. Interesting. Is there a glitch here in the book? I think the circuit is oscillating way too fast. So I'm going to try. Well, I don't have anything about the resistance, do I? everything's wired up correctly. And I know it's getting output, but the circuit is oscillating way too fast for us to even hear it. Yeah, the circuit's oscillating way too fast. I'll see, that's not going to cut it. So that's not going to work because we have too little resistance there. Unless the resistor is bad, which I doubt that it is. Simply put, the circuit oscillates way too fast to hear. Now there you go, that's Project 540, even though it didn't exactly work. It's just that it's oscillating, but it's oscillating so fast we can't hear it. It's way too high in frequency. But anyway, we're going to move on to Project 541, which is the Lighthouse. Yeah. So here we have project number 541, the Lighthouse. There it is in the book, and here it is on the board. So we got ourselves once again another oscillating circuit, but this time there is no output coming off of our transformer to a speaker or anything for it to listen to. In fact, this time we have our NPN transistor with our 100,000 ohm resistor as before, but this time we now have our 100 microfarad capacitor for the oscillation instead of something with a lower capacitance, which means this circuit is going to oscillate slow compared to the previous ones that generated oscillated faster, producing a tone. So we turn the circuit on, our LED, as you see there, lights up briefly and now starts flashing, and it's being limited by our 100 ohm resistor going in to our NPN transistor. So again, it's an oscillating circuit, but with that 100 microfarad capacitor there, the circuit oscillates to where it ticks about once every second. And we see that represented with our LED there. And again, if we change the capacitor and make it less, of course the LED will flash faster or may even be constant, and if we increase the capacitance, it will just flash even slower. So, similar to the previous project with an oscillator circuit, but no audible output from it. This time it's a visual with our LED. So that's Project 541, so now we're going to do Project 542, the Diode Wonderland. So here we are at Project 542, the Diode Wonderland. There it is in the book, and here it is on the board. So here we've got our B2 solar panel. As you can see, we also have a 6-volt supply on there. Of course, we'd have our other battery here, but our slide switch is there instead. And we have our D7 7-segment LED display. We have our green D2 LED, our red D1 LED, and our D3 standard diode. Kind of all connected in series here through our 100 ohm resistor, and then through both our PNP and NPN transistors connected together, in which you probably see is an interesting fashion because it's going through the bases and then through each one's collector and emitter. So with this project, with all the diodes in series like this, the thing with diodes is they all have a voltage drop. And the more diodes you add in series, the greater that voltage drop is, so that you need more input voltage to get these diodes to turn on. And in fact, although there is 1, 2, 3, 4 type of diodes here, there is in fact 6, because our NPN and PNP transistors in this configuration are also acting as diodes. So in total there are 6 diodes in this circuit. So we turn the circuit on. The solar panel is being used to boost the input voltage along with our 6 volts there, and there's just enough ambient light coming in that you can see that our little segment here on the 7-segment LED is lit up. And some of these LEDs are lit too, but they're very, very dim. So we need to bring some more input voltage by putting some more light on our solar panel. So by taking a flashlight If I shine it on the solar panel, you see that now our LEDs light up. And of course our press switch here activates other segments of our 7-segment LED, so if we push that, we get 0. But as you see, the 0 displays dimly compared to the single segment there, and that's because it's now sharing more current there to light the rest of those segments, and so it gets dim. And if I made this light even brighter, you see that now they really do light up nice and bright. So again, it takes a lot of input voltage to overcome the voltage drop of all these diodes in series as they are configured in this circuit. So that's project 542. So now we're going to look at project 543, the meter ranges. So here are project 543, the meter ranges. There it is in the book, and here it is on the board. So our circuit is pretty simple here. We have our meter, and it's in series with all these resistors and this speaker, and they're all individually switched except for our first one here, which is our 100,000 ohm resistor. So right now we got current flowing in a loop right here, and we can see that the needle is just above 0 on the meter set to its low setting, with the current flowing through our 100,000 ohm resistor from a 3-volt supply. If we add our L1 lamp to our 10,000 ohm resistor here, we add that to the circuit. Well, now the meter deflects pretty much all the way to 10 there, because now we have dropped the resistance down by putting these two resistors in parallel. So in this case, of course, our 2.5 volt lamp is not going to light with that much resistance, but in this case it's just acting like another 3-snap connector. Now if we switch our meter over to the high setting and turn on our slide switch, we now add our 100 ohm resistor into the circuit in parallel with our 10,000 and 100,000 ohm resistors, and again we get our needle on the meter just off the 0 mark there. And then if we add a big load to the circuit like our speaker here, which is only 8 ohms, press the press switch, and the meter deflects to about 7 on the high scale. So we go from increasing resistance down to decreasing all the way to a very low resistance item like our speaker, and that puts a lot of current on our circuit there. So that shows the various ranges of deflection on our meter. So that's project 543. So now we're going to look at projects 544 to 546, motor current. So here we are with project 544, the motor current. There it is in the book, and here it is on the board. And bring this in closer because it's a small circuit. So we've got our 3-volt supply with our press switch, our meter, and our fan there. Bring this up actually to about there. Get everything in view. So we're going to measure the current of our motor operating off of our 3-volt supply with our meter set to the high setting. So we press the press switch. Our meter deflects over to the right quite a ways, and then it comes back to about the 5 mark on our meter there as the motor gets up to speed. So when the motor's at 0, it's going to draw the most current on startup until it gets to a steady state when it's running. That's why the meter deflects so far over when we first start, until it gets up to speed, and then it returns to about the middle point there. So that's project 544. So project 545, we're doing our 2.5 volt lamp current. So we're going to take the motor out of the circuit and put our 2.5 volt lamp there in the circuit instead. And now we're going to press the press switch and measure our current with the 2.5 volt lamp in place. And you see it measures almost above the 2 mark there. Let me plug my camera battery in because it's complaining that it's needing charge before it completely goes out here during recording. Get this in here. There goes the book. So again, with our 2.5 volt lamp there, get just above the 2 mark there. 2.5 volt lamp lights up nice and bright off of our 3 volt supply. So now we're going to look at project 546, and that is our 6 volt lamp. So I'm going to take 2.5 volt lamp out, drop our 6 volts in its place. And now when we press the press switch, our 6 volt lamp comes on, and you see it's drawing a bit more current than the 2.5 volt lamp is. It's not lighting up as bright as our 2.5 volt lamp is, but it is drawing more current because this bulb is designed to run on 6 volts, whereas opposed to the last one is meant for 2.5 to 3 volts. So this one is a more powerful lamp, thus it's going to want to draw more current. So this one is just above the 3 mark there, almost between the 3 and 4 on our meter. So that is project 546. So the last one we're going to look at, bring this up, is we're going to look at 547, combined lamp circuits. So here we are at project 547, the combined lamp circuits. There it is in the book, and here's on the board. Let's come in a little bit here. So this is pretty similar to the project we had before, but we have our meter set to the high setting with our slide switch still using a 3 volt source, with our 6 volt lamp in series with our 2.5 volt lamp here, which then we can bypass with our press switch there, allowing us to completely go around the 2.5 volt lamp direct to our 6 volt. So when we turn on our slide switch, both lamps light up, and they're fairly dim, both of them. The 6 volt being worse off than the 2.5 volt one because of the voltage difference between the lamps themselves. And you see that our meter is deflecting just above the number 2 mark on there with both bulbs in series. Now if we press the press switch and bypass our 2.5 volt lamp, you see that our 6 volt lamp gets nice and bright, and we're hovering around the 4 mark on our meter. If I release the press switch and bring the 2.5 volt lamp back in series with the 6 volt lamp, the 2.5 volt lamp lights up again, the 6 volt goes back to being dim, and we go back to about 2 on our scale there. Because by having these lamps in series, we're inducing voltage drop across here, and so there's overall less current going through both lamps. But if I take this lamp out of it, then the voltage drop is only on the 6 volt lamp here, so it gets a good amount of current going through it, which allows it to be as bright as it is and then get more current through it. But again, with both lamps in the circuit, there's 2 points of voltage drop, so there's overall less current going through the whole circuit, and we see that on our meter. So that's project 547, and that concludes this set of Snap Circuits projects.